Imagine standing outside on the clearest night of your life. No city lights, no clouds, just you, the cold ground beneath your feet, and a sky so dense with stars it looks almost solid. You tilt your head back, and for a moment, you feel something ancient stir inside you, the same feeling that moved our ancestors to name the stars, to build pyramids aligned with them, to sail by them across open oceans. The sky feels close, intimate even, like something you could almost reach out and touch. Now imagine being told that most of what you see up there, most of those lights, are places you will never visit. Not because we lack the technology, not because we haven't built the right spacecraft yet, but because the universe itself has constructed walls around us, invisible walls, made not of stone or steel, but of physics, of time, of the fundamental structure of reality. The night sky is one of the greatest illusions in nature. It appears as a window, but it is actually a map of the unreachable. Tonight, we are going to pull back the curtain on one of the most astonishing and humbling facts in all of science, that the universe is so large, so ancient, and so governed by ruthless physical laws that the vast majority of what exists will forever lie beyond our reach. Not just beyond our reach today, beyond our reach forever. This is not a story about failure. It is a story about the staggering, almost incomprehensible scale of everything and the strange, beautiful loneliness that comes with understanding it. If the ideas in this video move you the way they move me, if you find yourself staring at the ceiling tonight, quietly stunned, consider subscribing to the channel and leaving a like. These videos take a long time to make, and knowing that people are out there genuinely engaging with this material is what keeps the work going. Now, let us get into it. Before we can talk about cosmic isolation, we need to get one thing absolutely straight. A light year is not a unit of time. It is a unit of distance. And it is a unit of distance so enormous that no human analogy fully survives contact with it. Light travels at approximately 299,792 kilometers per second. In 1 second, a photon of light travels a distance of roughly 300,000 kilometers. That is nearly 7.5 laps around the entire circumference of the Earth. In 1 minute, light crosses a distance of about 18 million kilometers. In 1 hour, it travels 1.08 billion kilometers. In 1 day, that number swells to about 26 billion kilometers. A light year, then, is the distance light covers in 1 full year. That works out to approximately 9.46 trillion kilometers, nearly 10,000 billion kilometers. If you were to drive a car at highway speed without ever stopping, it would take you roughly 10 million years to travel a single light year. Not 10 million days, but 10 million years. And yet, in the grand architecture of the universe, 1 light year is essentially nothing. Our nearest stellar neighbor, Proxima Centauri, sits about 4.24 light years away from us. That means the light entering your eye when you look at it tonight left that star roughly 4 years ago. You are not seeing Proxima Centauri as it is. You are seeing it as it was in 2021. This is one of the most profound and disorienting aspects of astronomy. Looking into the sky is the same thing as looking into the past. Distance and time in this context are the same. Travel further out, and the timescales become staggering. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light arriving from Andromeda right now departed during a period when our ancestors, early members of the genus Homo, were just beginning to chip away at the first stone tools. When we observe Andromeda through a telescope, we are watching a galaxy as it existed before human civilization, before agriculture, before language as we understand it. Go still further out to the edge of what our telescopes can detect, and you reach distances of 13 billion or more light-years. The light from those objects has been traveling since just a few 100 million years after the Big Bang. The universe itself was young when those photons began their journey toward us. There is something deeply strange about this. Every observation in astronomy is a form of time travel. The further we look, the further back in time we see. We have never observed the current state of anything beyond our own solar system. Everything we know about the cosmos is, by definition, historical. There is a hierarchy to this looking backward in time that astronomers call the cosmic distance ladder. Each rung represents a different technique for measuring how far away something is, and each rung reaches further into the past than the one below it. At the bottom of the ladder, we use parallax, the tiny apparent shift in a nearby star's position as the Earth moves around the Sunday. Then we use pulsating stars called Cepheid variables, whose brightness cycles at a predictable rate that reveals their true luminosity. Then we use type Ia supernovae, stellar explosions so consistent in their brightness that they serve as what astronomers call standard candles, objects of known brightness, whose apparent dimness tells us exactly how far away they are. Each technique unlocks a deeper layer of the past. The nearest stars, measured by parallax, show us the galaxy as it looked a few hundred to a few thousand years ago. The Cepheid variables carry us millions of years into cosmic history. The supernova take us billions of years back into an era when the universe was a fraction of its current size, and the galaxies we see today were younger, denser, more actively forming stars. And at the very limit of our instruments, the cosmic microwave background, the faint afterglow of the Big Bang itself, we see the universe as it was 380,000 years after its birth, before any star had yet ignited, before a single photon of starlight had ever been emitted. Every rung of the distance ladder is also a rung of a time ladder, and there is no rung that lets us see the universe as it is right now, in its entirety, all at once. We are, and will always be, observers of the past. But here is where things take a darker, more unsettling turn. These enormous distances are not merely the result of the universe being very big. They are the result of the universe being very big and actively working against our ability to traverse it, because the universe has rules, and those rules are absolute. Let us talk about the speed of light not just as a number, but as a fundamental law that shapes the entire structure of the cosmos. In 1905, a 26-year-old Swiss patent clerk named Albert Einstein published what would become one of the most consequential papers in the history of human thought. His special theory of relativity contained a radical claim: the speed of light in a vacuum is the same for all observers, regardless of their motion. This was not merely an experimental observation. It was a foundational principle, a cornerstone on which all of space and time are built. What Einstein showed, through elegant and unflinching mathematics, is that the speed of light is not just a very fast speed. It is the absolute maximum speed at which any information, any matter, any signal of any kind can travel through space. It is the universe's speed limit, baked into the deepest structure of reality. To understand why this limit exists, consider what happens to an object as it accelerates. The faster something moves, the more energy it requires to accelerate further. This is ordinary Newtonian physics. But Einstein showed that as a massive object approaches the speed of light, something extraordinary begins to happen. The object's effective mass, its resistance to further acceleration, does not merely increase, it increases without limit. As you approach the speed of light, the energy required to accelerate even slightly further becomes infinite. You cannot reach the speed of light, not with any finite amount of energy, not ever. This is not a technological problem. It is not a problem of engineering or innovation. It is a statement about the fundamental geometry of the universe. Space, time, and energy are woven together in a fabric that simply does not permit any massive object to reach, let alone exceed, light speed. Now, pause on this for a moment, because its implications are staggering. Our nearest stellar neighbor is 4.24 light-years away. If we somehow built a spacecraft that could travel at, say, 1% of the speed of light, a speed so far beyond anything we have ever achieved that it staggers the imagination, that journey would take 424 years. At 10% the speed of light, it would still take over 42 years. Even at 90% the speed of light, you are looking at nearly 5 years of travel time, one way, with no guarantee of anything waiting for you at the destination. And Proxima Centauri is the closest star. Our galaxy, the Milky Way, is roughly 100,000 light-years in diameter. To cross it, even at 99% the speed of light, would take 100,000 years of ship time, longer from the perspective of anyone left behind on Earth. The Andromeda Galaxy is 2.5 million light-years away. There is no version of physics, no matter how optimistic or speculative, in which a human being or any machine built by human hands could cross that distance in any civilizationally meaningful time. But wait, what about the time dilation effects predicted by relativity? This is where things get genuinely mind-bending. Einstein's equations show that time is not absolute. The rate at which time passes depends on velocity. The faster you move, the more slowly time passes for you relative to a stationary observer. This effect, known as time dilation, is real. It has been measured. GPS satellites have to account for it in their calculations, or the navigation systems would drift by kilometers every day. So imagine a spacecraft traveling at 99.9999% the speed of light. From the perspective of the people aboard, the trip to Andromeda might take only a few decades of their subjective time. In theory, a traveler approaching close enough to light speed could cross enormous cosmic distances within a single human lifetime from their own perspective. But here is the catch. During that same journey, millions of years would pass on Earth. The civilization that launched the mission would be ancient history, or more likely, extinct by the time the spacecraft arrived. There is no communication in the meantime, because any signal sent back would take millions of years to arrive. Any technology, any culture, any human connection would be separated by an unbridgeable gulf of time. Time dilation does not solve the problem of cosmic isolation. It transforms it. Instead of being a problem of physical distance, it becomes a problem of temporal severance. You can travel far, but in doing so, you cut yourself off from everything that existed when you departed. And this assumes we could even approach those velocities in the first place, which we currently cannot, by a margin of many orders of magnitude. The fastest human-made object ever launched, the Parker Solar Probe, has briefly reached speeds of about 692,000 kilometers per hour. The speed of light is about 1.08 billion kilometers per hour. We are traveling in our fastest spacecraft at roughly 0.064% of light speed. To reach the nearest star at that velocity would take roughly 6,500 years. These are not gaps that better engineering will close in a century or two. These are the fundamental physical constraints of the universe we inhabit. So we have established that the speed of light is an absolute limit, and that the distances involved in the cosmos are almost unimaginably large. But there is a third factor that makes the situation more extreme, still one that cosmologists only began to fully appreciate in the late 20th century. Space itself is expanding. This is perhaps the most counterintuitive idea in all of modern cosmology, and yet the evidence for it is overwhelming. In 1929, the astronomer Edwin Hubble observed that virtually all distant galaxies are moving away from us, and the further away they are, the faster they recede. This was not because they were flying through space away from us. It was because the space between us and them was stretching, like a rubber band being pulled apart at both ends. Think of it this way. Draw two dots on a deflated balloon. Now inflate it. Neither dot moves across the surface of the balloon, and yet the distance between them increases because the balloon itself, the fabric on which they sit, is expanding. This is exactly what is happening with galaxies. They are not moving through space in the ordinary sense. They are being carried apart by the expansion of space itself. Now, the expansion of space is not limited by the speed of light. Objects can move apart from each other at rates that exceed 300,000 kilometers per second, not because anything is traveling faster than light through space, but because the space between them is growing faster than light can cross it. This is a subtle but crucial distinction, and it has enormous consequences. In 1998, two independent teams of astronomers studying distant Type Ia supernovae made a discovery that stunned the scientific community. The expansion of the universe is not slowing down. It is accelerating. Something called dark energy, though the name tells us almost nothing about what it actually is causing the rate of expansion to increase over time. This changes everything. It means that galaxies, which are currently beyond a certain distance from us, are already receding faster than light can travel. We can still observe them, because the light they emitted long ago, when the universe was younger and smaller and they were closer to us, has had time to reach us. But any light they emit today will never reach us. The space between us and them is growing too fast for light to bridge the gap. This critical boundary is called the cosmic event horizon. It is the point beyond which, even if we could travel at the speed of light, we could never reach any object currently on the other side. Anything beyond our cosmic event horizon is effectively cut off from us forever, not just practically, fundamentally. No information, no light, no signal of any kind from those regions will ever reach us again. And as dark energy continues to accelerate the expansion of the universe, this horizon is slowly shrinking toward us. Galaxies that are today just barely within our observational reach will eventually cross the event horizon and vanish from the observable universe forever. Over billions of years, the night sky will gradually darken as one galaxy after another recedes beyond the point of no return. In the far future, trillions of years from now, an intelligent civilization in what is now our Milky Way galaxy might look out at the universe and see nothing beyond a few gravitationally bound nearby galaxies. The rest of the cosmos, hundreds of billions of galaxies currently visible to us, will have vanished behind an impenetrable veil of accelerated expansion. They will have no way of knowing that the universe is as vast as it is. The evidence will simply be gone. This is not speculation. It is the straightforward implication of the physics we have measured, tested, and confirmed. The universe is not merely large. It is actively separating itself from us, piece by piece, forever. Here is a thought experiment. Imagine you are standing in the middle of a vast, flat plain, perfectly level in all directions, stretching to infinity. Because you are standing at a specific height, let us say you are 1.7 meters tall, your ability to see across that plain is limited by your horizon. Beyond a certain distance, the curvature of the Earth means that even a perfectly flat, perfectly transparent plane will hide objects from view. Move higher, and your horizon expands. But there is always a horizon. There is always a limit to what you can see from where you stand. The observable universe is something like this. We sit at a specific point in space and time. Light travels at a finite speed. The universe has a finite age, approximately 13.8 billion years. This means that there is a limit to how far light could have traveled since the universe began. Any object beyond that limit has simply not had time to send light to us yet. The observable universe is a sphere centered on us, with a radius defined by how far light can have traveled in the history of the cosmos. But here is where it gets more complex. Because space has been expanding since the Big Bang, the objects that emitted the oldest light we can receive are no longer where they were when they emitted it. A galaxy that emitted light 13 billion years ago, when it was relatively close to the region of space that would become our Milky Way, has since been carried by cosmic expansion to a much greater distance. The edge of the observable universe, the surface of last scattering, essentially the afterglow of the Big Bang itself, is currently about 46 billion light-years away in every direction. Even though the universe is only 13.8 billion years old, the observable universe then spans a diameter of roughly 93 billion light-years. It contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars. The number of planets is beyond any count meaningful to human intuition. And yet, and this is the thing that should make your head swim, the observable universe is almost certainly not the whole universe, not even close. Most cosmological models, including those supported by the detailed structure of the cosmic microwave background radiation, suggest that the universe extends far beyond what we can observe. Some models suggest it extends so far that the observable portion we inhabit is an almost inconceivably tiny fraction of the whole. Certain inflationary models of the early universe predict that the total extent of the cosmos could be 10 to the power of 23 times larger than the observable universe or more. Some models suggest the universe is genuinely infinite. Think about what that means. If the universe is infinite, then everything that can happen does happen infinitely many times, in infinitely many places. There are infinitely many copies of you, reading words almost exactly like these, in galaxies scattered across a space too large for mathematics to make meaningful. The observable universe, with its 2 trillion galaxies and uncountable stars, becomes a vanishingly small island in an ocean that has no shore. But even if the universe is merely finite and very large, the portion we can ever observe or reach is bounded. We live inside a cosmic bubble defined by physics and time. Outside that bubble, things are happening that we cannot see, will never see, and can never influence. And the bubble, as we have discussed, is shrinking. There is something philosophically vertiginous about this. We often think of ignorance as a temporary condition, something that education, exploration, and technology can eventually overcome. But the structure of the universe guarantees that there are regions of reality about which we will remain permanently ignorant, not because we are not clever enough, because the laws of physics forbid it. Let us be precise about what we mean by permanently unreachable, because it is worth dwelling on this at length. In the history of exploration, humanity has repeatedly encountered barriers that seemed absolute and then found ways around them. Oceans that appeared to be the edge of the world were crossed. Mountains that seemed impassable were climbed. Even the atmosphere, that thin skin of air that kept us earthbound for the entirety of our evolutionary history, was eventually pierced. We went to the moon. We sent probes to the edge of the solar system. We are, as a species, relentlessly creative in the face of physical obstacles. But the barriers imposed by the speed of light and the expansion of space are different in kind from any obstacle we have faced before. They are not engineering problems. They are not resource problems. They are not problems of courage or determination. They are written into the mathematics that governs the behavior of energy, matter, space, and time. Consider the nearest galaxy cluster of significance, the Virgo cluster, about 53 million light-years away. With the most optimistic, plausible propulsion systems, physicists have seriously considered nuclear pulse drives, solar sails, even theoretical antimatter rockets. A journey of 53 million light-years would take tens of millions of years at minimum, and more likely hundreds of millions. During that time, the destination itself would continue to recede due to cosmic expansion. For many galaxy clusters, the expansion is fast enough that even a theoretical spacecraft traveling at a significant fraction of the speed of light could never catch them. To be specific, there is a boundary in the universe called the Hubble sphere, beyond which galaxies are currently receding from us faster than the speed of light due to expansion. This boundary sits at roughly 14 billion light-years. Objects beyond it are, in principle, reachable because the universe's expansion is not perfectly uniform, and the Hubble sphere is not the same as the cosmic event horizon. But the cosmic event horizon, roughly 16 billion light-years away, marks the true point of no return. Anything currently beyond it, traveling at the speed of light in its direction, will never arrive. The destination will always be receding faster than you can approach. Of the roughly 2 trillion galaxies in the observable universe, we will only ever be able to, in principle, reach a few 100 billion, those within our local cosmic neighborhood, gravitationally bound to us, and thus not carried away by expansion. Everything beyond that, the vast, overwhelming majority of what exists, is not just far, it is gone. Functionally, permanently, completely separated from us by the structure of space-time itself. And remember, this is just what is in the observable universe. If the universe is vastly larger than what we can see, then the fraction of total reality accessible to us shrinks further still toward what is effectively zero. There is a concept in physics called the multiverse, the idea, taken seriously by a significant number of theoretical physicists, that our universe is one of an enormous or infinite number of universes, each potentially operating under different physical laws. These other universes, if they exist, are entirely inaccessible to us, not merely far away, causally disconnected. No information can pass between them and us. They might as well not exist from any practical standpoint, except that their existence would speak to something profound about the nature of reality. Even within our own universe, then, the unreachable is not merely a distant outpost, it is the overwhelming majority of everything. There is a question that has haunted scientists, philosophers, and anyone who has spent serious time thinking about the universe, and it dovetails with everything we have been discussing in ways that are rarely acknowledged. It is a question first voiced with elegant simplicity by the physicist Enrico Fermi during a casual lunch in the summer of 1950. Fermi was discussing the possibility of extraterrestrial civilizations with colleagues, and he asked, with characteristic directness, "Where is everybody?" The logic behind the question is straightforward. The universe is roughly 13.8 billion years old. Our sun is only about 4.6 billion years old, which makes it a relative newcomer. There are stars in our galaxy that formed 10 or 11 billion years ago, stars that had billions of extra years to develop planetary systems, to potentially nurture life, to allow that life to evolve into something capable of technology. If even a small fraction of those ancient star systems developed civilizations, those civilizations would have had a multi-billion-year head start on us. In that time, even at modest fractions of the speed of light, a sufficiently ambitious civilization could have colonized the entire Milky Way many times over. And yet we see no signs, no signals, no megastructures, no evidence of any kind. The galaxy is silent. This is the Fermi paradox, and for decades it has been addressed with a catalog of proposed solutions, the so-called great filters, the idea of rare earth, The possibility of civilizations destroying themselves before reaching interstellar capability, or the notion that spacefaring civilizations simply choose not to signal. Each of these explanations is fascinating in its own right. But there is one aspect of the paradox that the physics of cosmic isolation makes newly sharp, and it is rarely stated as directly as it deserves. Even if intelligent civilizations are common, even if the galaxy is teeming with them, the barriers imposed by the speed of light and the geometry of cosmic expansion mean that civilizations separated by more than a certain distance can never meaningfully interact. They can never trade goods, share knowledge in real time, or collaborate on anything. A civilization 50,000 light-years away could send us a signal, and we would receive it 50,000 years after it was sent, and any reply we sent would arrive 50,000 years after that. The original civilization might not exist anymore. Its language, culture, and technology would be unrecognizable. The exchange would be a kind of cosmic message in a bottle, sent across a gulf so wide that both shores have transformed by the time anything crosses. Now extend this further. The cosmic event horizon means that civilizations beyond approximately 16 billion light-years are not just distant in the way that makes communication slow, they are absolutely, permanently disconnected from us. No signal they ever send will ever reach us. No signal we send will ever reach them. We are separated not by distance in the ordinary sense, but by the topology of an expanding universe. This means that even in the most optimistic scenario, a universe genuinely full of intelligent life, each civilization exists effectively as its own island. The unreachability of the cosmos does not merely affect us. It affects every mind, every civilization, every conscious arrangement of matter in the entire universe. Isolation is not a local condition. It is a universal one. There is something both humbling and oddly consoling about this. If we are lonely, it is not because we are uniquely unlucky or uniquely obscure. It is because the universe itself is structured in a way that enforces solitude. Every conscious species that has ever wondered about what lies beyond its horizon has faced the same wall of physics, the same speed of light, the same expanding space, the same cosmic event horizon drawing its quiet, inexorable boundary around each pocket of awareness. We are alone together, in a manner of speaking, with every other mind in the cosmos separated by the very laws that make existence possible. We have talked at length about the universe as it exists now, but the physics of cosmic isolation does not sit still. It evolves, and the direction it evolves in is one that future civilizations, if any survive long enough, will find increasingly stark. The universe is old, but on astronomical timescales, it is not yet very old. It is, in fact, still in what cosmologists call the stelliferous era, the age of stars. Our sun is a middle-aged star, roughly halfway through its roughly 10 billion-year lifespan. Most of the stars in the sky are in similarly vigorous phases of their lives. The night sky, as you know it, thick with starlight, is a relatively youthful thing. But stars are not permanent. They burn through their hydrogen fuel and die. The most massive ones explode as supernovae within a few million years. Medium-sized stars like our sun swell into red giants, and eventually shed their outer layers, leaving behind cooling white dwarfs. The smallest, most miserly stars, the red dwarfs, burn so slowly that they will persist for trillions of years, long after every star like our sun has gone cold. In about 5 billion years, our sun will reach the end of its life as a hydrogen-burning star. It will expand, engulf the inner planets, and eventually collapse into a white dwarf, a dense, cooling ember that will persist for hundreds of billions of years before slowly fading to darkness. Earth, if it still exists, will be long gone. But on even longer timescales, something more profound happens to the universe as a whole. As the stelliferous era comes to an end, roughly 100 trillion years from now, the last stars will exhaust their fuel and go dark. New star formation will cease, because the gas and dust that form stars will have been either locked up in stellar remnants or dispersed beyond recovery. The universe will enter what physicists call the degenerate era, populated by white dwarfs, neutron stars, and black holes, with almost no light at all. In this far future universe, any civilization that somehow survived would look out at a sky of almost complete darkness. The galaxies that we see blazing with the light of hundreds of billions of stars would be cold, dark, diffuse collections of dead stellar remnants. And due to the ongoing expansion of space, even those dead galaxies beyond our gravitationally bound local group would have long since receded beyond the event horizon, invisible and inaccessible for billions upon billions of years. The isolation that we experience, now limited and partial, counteracted by the brilliant light of a cosmos still full of active stars, would be nearly total. A civilization in the degenerate era would inhabit a universe that has, in a very real sense, retreated from them. The evidence of the Big Bang, the cosmic microwave background, would by then be redshifted to wavelengths so long as to be undetectable. If that future civilization had not inherited a scientific tradition describing the early universe, they might have no way of deducing that the Big Bang had ever occurred. The universe would appear static, cold, and near empty, with no observational evidence of the grand cosmic history that preceded their existence. This is a thought that the cosmologist Lawrence Krauss and others have pointed to with genuine alarm. We are, in a cosmic sense, living in a golden age of observation. The evidence of cosmic history is all around us, written in the light of a billion galaxies, in the microwave hiss of the early universe, in the specific abundances of hydrogen and helium left over from the first 3 minutes of time. Future civilizations, if they exist at all, may not have access to this evidence. They will be locked inside a universe that has hidden its own history from them. In this context, the science we do today takes on a quality that goes beyond ordinary curiosity. Every measurement we make, every model we build, every cosmological discovery we record is a form of preservation, a note left for minds that will inherit a colder, darker, more isolated universe than the one we inhabit. The light-filled sky we see tonight is not permanent. It is a condition of the early universe, already fading, already beginning its long retreat. We are, without exaggerating, living through the best time there will ever be to observe and understand the cosmos. The window is open. It will not always be. Now we arrive at the question that quietly underlies everything we have discussed. So, what does this mean for us? For most of human history, the answer to, "Is there something out there?" has been framed as a question about the unknown, something we might one day discover, catalog, and understand. The scientific revolution gave us tools. The space age gave us reach. And our inherent optimism as a species told us that the frontier is always temporary, always movable. But the physics we have been discussing suggests something more final. The cosmos is not merely unknown. Most of it is unknowable, unreachable by any agent that originates here, governed by distances and expansion rates that make the word barrier seem almost quaint. The frontier, in the case of the cosmos, is not a place we will one day push beyond. It is a permanent horizon, and in certain senses, it is drawing closer. This raises a cluster of philosophical questions that physicists, philosophers, and thinkers of all kinds have begun to wrestle with seriously. The first is about significance. Does it matter that most of the universe is unreachable? Some would argue that it diminishes us, that we are trapped in a tiny cosmic backwater while the vast majority of existence unfolds beyond our perception or influence. The universe is indifferent to us, proceeding according to its laws without regard for what we observe, discover, or do. In this view, cosmic isolation is a kind of existential demotion. But there is another way to hold this. The great 20th century physicist and educator Richard Feynman once observed that the vastness of the universe does not diminish the beauty of a flower. What we know about the biochemistry of the flower, its evolutionary history, the physics of how light interacts with its pigments, all of this adds to its beauty rather than subtracting from it. Knowledge does not reduce wonder, it deepens it. The same might be said for cosmic isolation. The fact that we inhabit this particular bubble of observable reality, bounded by the speed of light and the expansion of space, does not make what is inside the bubble less extraordinary. We exist in a universe that has organized itself over 13.8 billion years into structures of breathtaking complexity. Stars, planets, galaxies, black holes, and at least one rocky world where chemistry somehow became biology, and biology somehow became consciousness. That consciousness is now capable of looking out at the universe and measuring it, modeling it, and feeling moved by it. The universe is, as far as we know, not doing that anywhere else within reach. We might be utterly alone in the observable cosmos. We might be one of countless civilizations. We genuinely do not know. But either answer is astonishing. The second philosophical question concerns purpose. If most of the universe is permanently inaccessible, does that change what we should value or pursue? Some find in this the logic of turning inward, of attending more carefully to Earth, to each other, to the fragile and finite world we actually inhabit. If we cannot go out there, perhaps the lesson is to tend more carefully to here. Others argue that the unreachability of the cosmos makes the ambition to explore it more noble, not less. There is something deeply human about reaching toward a horizon you know you cannot cross. We build cathedrals too large for any one generation to complete. We plant trees whose shade we will never sit in. We write music for audiences not yet born. The impossibility of full exploration does not negate the value of trying, or of understanding, or of sending our knowledge as far as it can travel, even if we cannot follow. The third question is about time itself. Everything we have discussed operates on scales that dwarf human experience so completely that our intuitions break down. The universe is 13.8 billion years old. Complex life has existed on Earth for perhaps 600 million years. Modern Homo sapiens have been around for perhaps 300,000 years. Recorded human civilization spans roughly 5,000 years. A human life, your life, is a flicker of something shorter than the resolution of any cosmic clock. And yet here you are, comprehending this, feeling the weight of it. That strange ability to grasp scales so far beyond your own is one of the most remarkable things about conscious minds. We are physically tiny and temporally brief, but we are cosmologically aware. We know we are brief. We know the scales involved. We are, as the astronomer Carl Sagan observed, the universe knowing itself. There is a fourth question, one that tends to surface quietly, often in the middle of the night after someone has spent too long thinking about everything we have covered. It is a question about knowledge itself, about whether understanding something unreachable has value. Consider how much of what we know about the cosmos is, in a practical sense, useless. The discovery that a galaxy 12 billion light-years away contains a quasar 10 billion times the mass of our Sun does not help anyone grow crops, or cure disease, or build a better bridge. The measurement of the cosmic microwave background's temperature to 5 decimal places has no direct technological application. The debate over whether the universe is truly infinite or merely very large will never affect the price of anything, the outcome of any election, or the resolution of any conflict between nations. And yet cosmology, this strange, abstract, impractical pursuit of knowledge about things we can never reach, commands the attention of some of the sharpest minds our species produces. It motivates billion-dollar telescopes. It fills textbooks. It fills conversations. It fills videos like this one, watched by people who have no professional need for the information and who will never directly apply it. Why? The answer, if you press people, tends to circle back to something almost impossible to articulate cleanly. It is something about knowing where we are, about orienting ourselves in the largest possible frame. The philosopher Blaise Pascal, writing in the 17th century, was struck by the terror of infinite space, the silence of the eternal voids. But there is a counter-tradition, equally deep in human experience, that finds in that same vastness not terror, but liberation. If the cosmos is immense, then our local troubles, our temporary failures, our small cruelties, and smaller vanities are brought into a proportion that makes them easier to hold. The universe is large enough that there is room for perspective. The unreachability of most of the cosmos might, in the end, be one of its most important gifts to us. It tells us, with mathematical precision, that we cannot go everywhere. We cannot know everything. We cannot escape the specific, particular, irreplaceable world we were born into. And perhaps, in that confinement, in that enforced intimacy with one small planet and one brief civilization, there is something worth attending to very carefully. There is something almost unbearably poignant about that. In a cosmos whose regions are cut off from each other, perhaps forever, the fact that matter has organized itself in this corner of the Milky Way into beings capable of caring about what lies beyond the cosmic horizon is itself a kind of miracle, or if that word makes you uncomfortable, a kind of staggering improbability. We will not reach those distant galaxies. Their light reaches us instead, crossing unimaginable distances to fall on human eyes. The cosmos comes to us in the form of photons that have been traveling since before the Earth existed. And in receiving that light, in measuring it and decoding it and building the mathematics to understand what it means, we do something no other species we have ever encountered has done. We push our minds to the limits of what can be known. That is not nothing. In a universe defined by limits, it is perhaps everything. Step outside tonight if you can. Find a dark place away from the city. Let your eyes adjust to the dark. The stars you see are close ones, mostly within a few thousand light years of you, the bright and middle distance of our own galaxy. The faint smear of the Milky Way crossing the sky is the combined light of hundreds of billions of stars, most of them so distant their individual light is invisible, but their collective glow is not. Somewhere in the southern hemisphere sky, you could see the Magellanic Cloud satellite galaxies of the Milky Way, roughly 160,000 light-years away. In the northern sky, in autumn, you can find Andromeda, a faint smudge visible to the naked eye that represents 2.5 million light-years of distance and 1 trillion stars. All of it, every point of light you can see, sits within the small neighborhood of the cosmos accessible to your unaided senses. Beyond it stretches the observable universe, its 2 trillion galaxies receding in all directions into distances that dissolve into mathematical abstraction. Beyond the observable universe stretches more space, possibly infinite, containing regions that the laws of physics have permanently hidden from us. You are standing on one rocky world, orbiting one ordinary star, in the outer arm of one galaxy among 2 trillion. Your horizon, in cosmic terms, is almost vanishingly small, and yet you know this. You can hold the full shape of the cosmos in your mind, at least in outline. You can feel the weight of the distances. You can sit with the strangeness of a universe that contains more unreachable places than any mind could catalog, and still find it beautiful. The universe is unreachable. Most of it is gone from us, forever, carried away by a dark energy we barely understand, into distances no light will ever bridge. And still, it has given us this, one small world, one thin atmosphere, one narrow window of geological and evolutionary time in which minds like ours could exist. We are the universe pausing to look at itself, briefly, from one improbable vantage point, in the short interval before the stars burn out and the dark reclaims everything. If that does not fill you with something close to awe, I do not know what will.